Everyone. It is my great pleasure to welcome you all on the behalf of the entire organizing team of the prestigious GYAN, that is Global Initiative of Academic Networks course titled Chain of Things, a course on blockchain and IoT. We are honored to have esteemed faculties, distinguished guests, and all the participants joining us in this academic endeavor. Now, to mark the beginning of this enlightening journey, we shall now proceed with the lamp lighting ceremony, a revered tradition symbolizing the dispelling of darkness and the illumination of knowledge. May this course serve as a catalyst for meaningful learning, collaboration, and innovation in this field. I would now like to invite our esteemed guest to grace the stage and join us for the lamp lighting ceremony. Please, sir, please, ma'am. सर ऐसे ही पढ़ेगी भी बात नहीं सर कोई बात नहीं ऐसे करेगी Thank you so much.
Department, Professor S.B. Singh, Local Coordinator of IIT GAN Program, Dr. Sarang Gumfekar, Associate Dean, Continuing Education and Outreach Activities, my departmental colleagues and my dear participants. I am Sujata, Course Coordinator of the GAN course on Chain of Things, a course on blockchain and IoT. On the behalf of IIT Rupar, I welcome you all. It is a true pleasure for me to welcome you for the 5 days GYAN course on Chain of Things. The Global Initiative Academic Networks GYAN is a program of the Ministry of Education, Government of India. It is designed to tap the talented pool of scientists and entrepreneurs internationally to encourage their engagement with the Institute of Higher Education in India. I heartily welcome our Dean for taking time off for his busy schedule to attend this virtual meeting. He will join within short duration. He is on the way. It is my pleasure to welcome Professor Susmita Rooj from University of New South Wales, Sydney, Australia, who agreed our invitation for one of the valuable resource person for this workshop. I heartily welcome Professor Yasbir Singh and Head of the Department, Professor Nitin Aulak, my colleagues, my students who helped me in organizing this workshop. Last but not the least, I welcome and would like to express my heartfelt gratitude to all participants who sincerely committed to this event to make it a success. Thank you, one and all present here.
Dr. Nitin Aulak, HOD of the Computer Science and Engineering Department, IIT Roper, to share a few words with the participant. Please, sir.
Nice. So first of all, I'd like to welcome you all to this 5-day program on two very important topics, blockchain and IoT. So as we know, these days all systems are distributed in nature, and that raises a lot of security challenges which were not there earlier. and so definitely security becomes a very pertinent and important topic to study. So I'm sure that all of you will be able to get a lot of benefit from these 5 days of activity. Uh, it's a matter of great pride that we received really good response to this workshop. It's a glorious moment to extend our warm wishes on behalf of IT Rover to all of the participants. This event would not have been possible without the support of each and everyone here. We are really happy and honored to welcome participants from all over India. Uh, and yeah, as I said, it's a great opportunity to learn various aspects of these important topics. Uh, Another information I'd like to share is that this GIAN program is now handled by IT Hyderabad, and Dr. Anil Agarwal is the national coordinator of this program. And I also have a message by Director of IT Hyderabad, Professor B.S. Murthy, which I will read out. The program offers great opportunities for Indian students to closely interact with international experts for considerable duration. By participating in GIAN, students will gain invaluable insights, practical knowledge, and international perspectives that will enrich their academic pursuits and their future careers. So, without taking too much time, I hope that this workshop is very useful and fruitful to all of you. Thank you once again for attending. All the best. Thank you.
Constant support and continued guidance for this endeavor. Please, ma'am. Singh, local coordinator of the GIAN program at IIT Roper, to share few words with the participant. Please, sir.
Good morning and welcome to this GIAN course. So this GIAN program actually offers you an opportunity to invite a foreign expert. So that is the key, that we get the expert from outside who is well known in the field. And then she comes here, or the expert comes here, and the students who participate in this workshop and course, they actually get an opportunity to directly interact. Not only listen to her, exposed to labs and other techniques, rather interact. And we believe that basically that is very, very important and crucial part of learning, where you get a chance to interact with the expert. So this GIAN courses offer that opportunity to you. And I know that our expert is well renowned in this in her field, and you will learn a lot about by just interacting with her. And it also offers an opportunity, because once the expert is here, he or she will meet with our faculty, our students. So that also opens up an opportunity for future collaborations. Then exchange visit by students. So it offers in that sense a wonderful opportunity. And actually I appreciate, thank our expert for taking the time to visit our campus. And then I also thank Dr. Nitin and Dr. Sujata for arranging all this. But more than that, IIT Roper has a very, very active program of GIAN course. So we are actually running around 8 GIAN courses. CSE is participating, Math is participating, Physics is there. Almost every department is there. So if you go to our website, you will learn different courses that are there. I invite you to join us. If you have any feedback, any suggestion, please give it to us, me or Dr. Sujata, and we will try to implement it. Once again, welcome to GIAN course, and I wish you the best. Thank you.
The organization of this course. Please, sir. Sushmita Rooj, Associate Professor, UNSW, Sydney, Australia, Course Instructor of the GIAN course. Please, ma'am.
Okay.
thankful to all the participants who had joined us in this program, and I am also thankful to all the dignitaries present here to spare their time, to spare their valuable time to join us today. Now, without a further ado, I would like to request Dr. Sushmita to deliver her session on consensus protocols for blockchain. And we would like to say, sir, you will have a tea for which is available outside. Please join us.
Thank you so much.
And if you have any suggestions, please.
Sure, thank you. I did have a look into some of the feedback that you put on the.
You have to mute your system.
Okay.
Okay.
Told to put a little bit more examples and so on. So I'll try to do it today afternoon, and what we'll do is like we'll keep the pace. Keep the pace normal like yesterday. We will also make sure that you have, the questions that you have, we can take it then and there. And you did ask me to put some and, read further on, follow up on the reading. Okay. Start, right? Today. So before we get started, let's have a brief recap of what we did yesterday. So we saw what was a little bit about the history of blockchains and very basic ideas that are important to build blockchains. So we did go a bit into cryptography yesterday. So today we'll go a little bit into the consensus algorithms for blockchains. Afternoon, you had some hands-on practice with smart contracts, writing smart contracts, and so on. Okay. Fine, I'll just try to see if we can minimize this. Not sure if we can hide. Anyways, maybe I don't know how to hide this. So, in this lecture, we'll revisit some of the old things that we studied yesterday and the need for consensus. And then we'll talk specifically about Nakamoto consensus. Nakamoto, if you remember, Satoshi Nakamoto was the person who actually, is a proposer of the Bitcoin. And then we'll talk of a very prominent consensus algorithms for blockchain, which is called the proof of stake blockchains. And we'll talk about how Ethereum does proof of stake. And there's some very interesting observations to make there. And then we'll talk about, proof of X. And X is like, it could be many things. And at this point, this proof of something is not very clear. So let us talk about that. So yesterday we saw this picture. This is essentially how blockchains work. All the nodes are running have the ledger, and they are running the smart contracts. So yesterday when you did the smart contracts, and you might be thinking like, who is executing the smart contracts? So it is each and every node who is running the blockchain client. So is running the smart contract. What it means is that the same blockchain, the same copy of the blockchain is present in all the machines that are running this software. So we also had a look into how blockchains work. So the first step is to construct transactions, right? What is the next step? Does anyone remember? Huh? Yeah, so group the transactions together and construct blocks, right? So you might be asking this question, who is taking the transactions and who is grouping it, right? That's a most fundamental question. So this happens, and this is different. This is how different blockchains work. Different blockchains deal with this in different ways. But loosely, all the transactions that are happening in the network. So, for example, I've made a transaction, so I'm broadcasting it to everyone in the network. And there are specialized nodes who are called miners or validators who will actually take all these transactions, keep a track of these transactions together in something called a mempool. Okay, so the mempool is a place where all the transactions are kept. And from this mempool, they will take a set of transactions and put them in a block. So this is something that I didn't say yesterday. So it was like very abstract yesterday. I said just take the transactions and put them in the block. So who does this? It is the miners or the validators. Miners in the case of Bitcoin. Bitcoin uses this terminology, miners. So the miners would take all these transactions, and from these set of transactions it has received within a period of time, it will take a set of transactions and put them in a block. Okay. Is this clear? Okay. And then what happens once we have a block? The miners broadcast it in the whole network. Okay. So this part is pretty simple. Any miner who has constructed a block, you can the miner essentially puts it in the network, and then yeah, you're verifying these blocks. Who is verifying these blocks? So there are nodes who are validating these blocks. And if you think of the client, whatever client it is, a blockchain client, they have the capability of looking into the blocks, look at each of these transactions, check these transactions, check all the other information. And this is something that I'm going to show in today's, in the afternoon when we really see how the transactions look like in real time. So the blocks are verified, and then in the last step, if it is a valid block, it is added to the blockchain. Now here are some of the interesting questions that you might be asking. Okay, any doubts over here? Who is adding the block to the blockchain? Any guesses? Who is adding the block to the blockchain? Verified, yeah. Someone who verified the block is adding the block to the blockchain. And do you have any questions on that? If there are multiple verifiers, whose block will you take?
Trusted one.
Huh?
Someone who can be trusted.
Who can be trusted? Okay.
Someone who got the reward.
Someone who got the reward. Okay. So, someone who is trusted. How can you trust a person? How can you trust a node?
History.
Transaction history. And then, reviewing them, yes. Looking into the transaction history or, the history of action. So you see yourself, every time you are thinking, you are coming up with interesting ideas, right? That's the point. So different blockchain does it in different ways. The same thing, just adding the block to the blockchain is done in several different ways. And today we are going to see some of the options that different blockchains take to first construct the block, verify the block, and then add the block to the blockchain. So all these steps are done differently in different blockchains. And depending upon how they are done, you can essentially get some gain in performance sometimes again in the amount of communication overhead. When I say communication overhead, it is essentially how much data or information you are sending across the network. Because in computer science, you have a few things, right? Computing, communication. So computing means how much I'm computing on my device. And communication overhead is essentially the size of the data that I'm sending. So when I'm saying I'm broadcasting information, essentially it's how much data I'm sending across the network, right? Okay. So we'll see some of the ways these are done in different blockchains and the unique benefits each of them get. So, the good thing about this blockchain space is that there has been designs. I've been in this space for many years now. Like I started in 2014, so it has been over 11 years I'm doing this. And I've seen things evolve. I've seen blockchains which were very prominent and they died. And then there were emerging new blockchains. Some have withstood the ravages of time, like Bitcoin, Ethereum. But there's something to think about how they were designed, which gave them that competitive advantage, and how blockchains have also evolved over a period of time. It's a very short period, like 10 years in the history of computer science. It seems pretty small. Or for computer science, things are always very very recent. Everything is very recent, right? But still, 10 years is a very very short time. But we have seen a lot of things happen. So we'll see how what are the different ways this can be dealt with, this problem. So if you remember, yesterday we also saw this, that we asked this question, that how would, if Alice is transacting with Bob, how would I show a couple of things? How would I show that she has enough in her account? And how does she prove authority to spend it? So these are some things that we have to see. And what we said is that along with the transaction, you put the signature on the transaction. Alice puts a signature on the transaction to say that she has made this transaction and she has authority to make this transaction. She has enough money to make this transaction. So the other thing that we also talked about was this part, where blocks are being verified and blocks are added. How does one deal with this? So let us look into some of the options that are available and some of the blockchains, how they have done this, how they have addressed this problem. So few things that we asked yesterday is that what is the incentive of a node to participate? So when we were talking, so you said the two nodes, they are both competing to add their blocks on the blockchain. And you would look into the history or look into the behavior to decide which to add, right? But think from the nodes who are generating the blocks. What is their incentive, first of all? If you don't give me any incentive, why will I work, right? So it's not an altruistic society, right? It's, at least in the blockchain space, it is not an altruistic society. Blocks are made, and this essentially consumes power and electricity. So computing, so you have to give them some incentive. So incentivization becomes a very key question, and different blockchains will do it different way. We will see first how Bitcoin does it. And then a puzzle that a node has to solve in order to create a block. So for example, if two nodes are competing to generate a block, and they know that they will get a reward. Suppose you say that I'll give a reward if you create a block. At this point of time, how many of you want rewards? I see only 2-3 hands. You all don't like rewards, right? Is it? Okay, so we all like rewards, mostly. But to get that reward, you have to do something, right, to get the reward. So that is where nodes essentially have to solve a puzzle. Not only have they take the blocks and they verify the contents of the block, but they have to also solve a puzzle. And this is essentially computational work that they have to perform. So if there are two nodes, the only thing, in order to be rewarded, they have to do this computational work is something that they will do only if they're serious about it, right? And they would get the reward only if they have verified all the blocks and they have solved a computational difficult puzzle. So this is also called a lottery, essentially, because this puzzle is very random. You cannot guess what puzzle will be given to you, and then you have to solve it. So what is this puzzle? What does this puzzle look like? And why do I say it's like you really have to work for it? So in the case of Bitcoin, wait a minute, it's taking time to sync. Yeah. We'll see that what this particular puzzle looks like. So the puzzle essentially says that you take the block, you hash the block. There's actually a lag, so it's still not visible. It will come. So you take the block, you hash the block, and the hash value should be less than some predefined difficulty level. Yeah. So essentially, this is a puzzle, and I'm going to show this M and R. At this point, you might be thinking, what is M, what is R, and I'll show you what it is. But think about it, if you are given a puzzle where you have to hash a message concatenated with some randomness. So R is some randomness. So when I say random, it is like, think of it as something like, you're tossing a coin. You can get any output, right? It can get a head or a tail. So this R is essentially a random value, and M is a message. So you have to hash the message along with the randomness such that the value is less than some predefined value, Z. Okay? So Z is decided prior to this start of the protocol. Okay? And this C is called the difficulty level. Now note that if you take a hash function and you hash a value, R concatenated with M, there's no guarantee that the output would be less than R, right? Less than Z, right? Because when we talked about hash function, the output of the hash function looks completely random. So we don't know whether the value will be less than Z. So then what can we do? What can we do? And our message is the same. Message is the same. What we can do, we can simply keep changing the value of R. We just say, maybe take R to be 1, 1 concatenated with M, then 2 concatenated when we just increment it, by 1. And every time you check the hash value, check if it is less than Z, right? So essentially, if your hash function, the output of the hash function would be large, and then depending upon the value of Z, it could be very hard for you to really predict what this value, which particular value of R will essentially give you this, will give you a solution to this puzzle. And that is why you have to keep on hashing many times till this equation is satisfied. R concatenated with M is less than Z is satisfied. So let's see what it looks like from Bitcoin structure. Now, what happens, if you remember, what happens, there's so much lag actually. Yeah, so this is the structure we saw yesterday. And if you remember, we had all the transactions, The transactions were put in the form of a Merkle tree, yes. And then you keep the root of the Merkle tree on the blockchain. And you have the previous hash value, hash of the previous block added in that new block. You see also this value called the nonce. Do you see it? So that nonce is at randomness. So I can change this value such that I can come up with a block whose hash value will be less than the value r. So let us show how this looks like. So this is essentially what we want to do. We will take the block, we will hash the block such that the value is less than z. And the z is the difficulty level, which can be adjusted from time to time. Okay? So now look at it. You have everything fixed for this particular block. You have the previous block, which is fixed. You have the root hash because you have chosen a set of transactions. The root will be the same. Root will be the same. So that is constant. Your timestamp is the one at which time you're preparing the block. But nonce you can keep on changing one after the other until you have the hash of this block to be less than z. Is this clear to everyone? So your r is essentially your nonce. You're changing the value of nonce until this equation is satisfied. I'll pause. Yeah, again. So you have to solve a difficult puzzle. Say, there are two miners who are competing. So if what they will be doing, they would actually have a set of transactions they want to put on the blockchain. So they would have some TX. Now for two miners, your set of transactions could be different. Your previous hash is the same. You were thinking like the timestamp will also be slightly different, but there's no guarantee that the hash of these, the block that it is created is less than z. So both of them will start competing and they will just go on computing hash of the block till it comes to this particular value. And because this hash function outputs are completely random, it's very difficult to predict what's going to be the output. And that is why, it's very hard to say, unless and until you do, you keep on hashing one at a time, it is very hard to say for what value will get this to be z. So that is why this gives the guarantee that, this is a computationally difficult puzzle and you have to spend enough resources to solve this puzzle. And that is what Bitcoin does. And this is called proof of work. I'm doing some work. I'm doing lots and lots of hash computation. Does this make sense? Questions, anyone?
Where they get the value of z?
Yeah. How?
Z value.
Yeah.
Whether it is
okay.
Constant or
yeah, it changes. So the difficulty level changes. And there's a particular formula that I'm not going to talk about. There's a particular formula. From time to time, Bitcoin adjusts that value of z so that it makes it harder and harder for nodes to solve this puzzle. If you go to a Bitcoin wiki, you will get all these detailed, formula to compute the value of z at that particular point of time. Okay, so this nonce is essentially a source of randomness. Z is called the difficulty level. And the hash function in this case that's used is SHA-256. The difficulty level is so adjusted that it takes approximately nodes 10 minutes to solve the puzzle. Okay, so depending upon the network conditions and there are other parameters, you can set the value of z, not you, it will be the system who sets the parameter z, and then miners can work accordingly. So note one thing, that once you have the block, anyone who is getting the block that the miners have created, everyone can check. Checking is very easy. Why is checking very easy? Because they can validate transactions very quickly, because there are about, say, 1,000 transaction or 2,000 transaction. It's not very hard. And then, previous hash is known to them. Timestamp, they can see what timestamp it is, the nonce value they can see, and they compute the hash of that particular block, and that's it. If the hash, just given a value m, hash of h of m is very quick. It takes only milliseconds. So verification of this, whether the puzzle is solved correctly or not, is very easy. However, solving the puzzle is very hard. Say, think about it. You think of a Sudoku puzzle. When you're trying to solve it, you are taking an effort to solve it, right? But once you see a Sudoku solution, you can quickly see whether it is a correct solution or not, right? So verification is very quick. Solving the puzzle is very hard. And it has been seen that the current Bitcoin network, it calculates about, 774 transaction hashes, million transaction hashes per second. So this is really too large. And the other thing to keep in mind is that every 216 blocks or 14 days, the difficulty level is adjusted. It is adjusted with some formula that is, I'm not talking about it, I don't remember it. But this is there in the Bitcoin wiki and you can have a look at it. Okay. If a miner is able to construct a block correctly, then it gets a reward. And at this time, it is around 3.125 BTC as of April 1st, 2025. So what happens is that every 4 years, this value gets, the BTC, the miner reward gets halved. So after 4 years, from 2024, 2028, it will again become half of 3.125. Yeah. So initially, I think it started with 25 BTC, then it became 12.5 BTC. 4 years later, then it became 6.25 and so on. And what Bitcoin wants is that, as time passes by, it will be self-sustainable and they don't have to give this reward, this substantial amount of reward. So this is because this is quite expensive. Okay. So, what we know is that the proof of work, the concept of proof of work, has been there for a very long time. As I said yesterday, it was used to detect spam. And that was long back when Dwork and Nar had proposed this to combat email spam. And it was used by Adam Back to do the same. And Bitcoin also Bitcoin uses this proof of work, which is a successor of Hashcash that Adam Back used. Yeah, so this is essentially a graph from this week. Not this week. I mean, this is the latest. I mean, taken in during this week, and you can see how these hash rates are increasing. At this point, it is 774.72 million terahashes per second, which is really, really a lot. And our normal machines cannot do these type of things. So we have to rely on really big supercomputers or special chips, which are specially designed to this sort of thing. So Bitcoin mining is extremely expensive. So if you think like, okay, fine, Bitcoin, which is valued at a few, its price fluctuates, but it's 3.125 Bitcoin will make me rich. Let's start. Let's try to be a node and mine some coins. It's not going to be easy because we don't have that resource to compete with the miners. Is this clear?
I have given the randomness value or whether it is a floating point or integer value, this is given by minus or it is automatically generated.
Okay, so the nonce essentially is an integer. It starts with 1 and then you can keep on adding 1, 2, 3, 4 and so on. So R is an integer, positive integer.
Given by minus.
Oh yeah, so it's not given. So miners will choose an R and compute. Yeah. Yeah, question.
Who is giving these rewards now?
Yeah. Who is giving the reward? The system is giving the reward. What is the system? Pardon?
And how do they get rewards like by mining? What they mine?
Yeah. Okay. The good question. What do they mine? They mine coins. It says mine because whenever you are creating a block, you are generating some new Bitcoin. That's why it's called mining.
The randomized blocks are given. Firstly, I give the correct answer, the equal to z. How it's possible?
Yeah. So it is not possible that the first go you will get the right answer. So you have to keep on doing the hash. So as I'm saying that there are so many hashes you have to compute. First time you compute a hash, it might be some value, it's not less than C. Second time you compute a hash, it might not be less than C. Third time you compute. So you keep on compute 100,000, million, and then, so many million hashes. Done? Is that clear? Clear? Okay. Okay. The other question is that from where am I getting it? Where does it generate, right? It looks very, suspicious, like from where am I getting? So it is, you think, because everything is digital, right? So your wallet will be credited with whoever, the miner's wallet will be credited with the miner's account will be, not wallet, I would say miner's account will be credited with this extra reward. Because it's not like, think like this, that the Reserve Bank of India is minting some, currency and giving it to you. Only that we don't have a central authority to give you the thing. It is a system. When I say system, it is the client. Client means a software. The software that is running, everyone's software, when a block is generated, everyone's software is working actually. Everyone is updating their, the list of blocks to the new block. It's happening in the software. Does that make sense? Because everything is, so you have a Bitcoin client. It is running on your machine, anyone's machine for that matter. When a new block is created, it is added. Because this is a little bit hard, I have struggled myself to really understand Bitcoin, or not just Bitcoin, any blockchain. So I can anticipate questions. Yeah, any more? Pardon?
What are the clients?
Client means a client software. You can think of a software that's actually running on your machine. That is called a Bitcoin client. How does it work? Just like any other software works. It has a piece of code, it is executed, and that's how it works. So in a piece of code, think of it as a piece of code. You have a piece of code, you have a hash function. Think of it, that you are doing a loop. You are running the loop, say so many tera, having million times or so many things. You are computing, changing the nonce one at a time and computing the hash, checking with the value of z. That's how. From no one, from the system. So essentially what is happening is that if you are a miner and you have solved this, your account is being credited with this. Yeah.
How the transfer is happening from sender should be there, receiver should be there.
No, not always. And I'm going to show you when we are looking into the transactions, when it is a reward time, it does not have a sender.
Is it like who are participating in the mining process, they are giving some money to
No, no. For this reward, if you look at a transaction, then you would see a sender and a receiver, multiple senders and multiple receivers. I'm coming to this. I'm going to show, when I show you the real data, I'm going to talk about this. But there's no sender when it comes to the reward. It's just a receiver receiving this thing. That is a transaction.
Client system generates.
Yes.
We are creating new Bitcoin. Is it right?
Yes. So if your block is accepted, you will get the Bitcoin.
So then, like, if the Bitcoins are increasing, so why not its value is decreasing? Like, if you have more Bitcoin, then due to inflation, like.
Oh, yeah, that's a good question. So the market mechanism for cryptocurrencies is something, honestly, it's beyond me. Honestly, I don't understand the economics of this, the market. There are many factors that make this cryptocurrency market extremely volatile. And honestly, I don't know. I mean, I will not give you a wrong answer. So I would rather pass this off.
And there is a hard limit of 21 million Bitcoin.
Is there? Okay. Fine. Thanks. So that is where they are saying that, it's getting half. And finally, they will just remove that reward. You see, understand why they are putting that hard limit? Because Bitcoin is mined in the system. So initially, Bitcoin started with nothing, 0. Then blocks are added. And every time a block is added, you are pumping in the reward value, right? Is this clear to everyone? So, and the reward value gets decreased. So there should be a limit, as you said. I don't know remember the limit, but as you said, there is a limit. That is where it's going to stop. So now it is 3.125, then it's going to be another 3.125 divided by 2, and so on. Yes.
So what you're saying is that the system is designed in a way that it automatically gets.
Yes, the system is designed in a way that automatically does it.
Whether the reward can be converted as a currency.
Yeah, that's a good question. Can I convert the reward as a currency? Of course. So there are exchanges which are called the cryptocurrency exchanges. So whatever you have in your wallet, you can take to the, you can go to the, yeah.
Is it like an organization or an application? Like to exchange it with money?
Yeah. So Bitcoin, this exchanges, these are regulated exchanges. There are many regulated exchanges where when you give this, it is just like any other exchange. Say Forex, if you have two different currencies, you go to a bank and they will exchange it. Just like that, they have, there are different exchanges which are running, and they are the ones that will take you, this currency, the cryptocurrency, and will give you the fiat currency.
Is it possible in India, ma'am?
I'm not too sure what are the regulations around. What are the latest ones? I don't know. At one point of time, it was not, I think they had something vague, like they were not supporting or they were not essentially saying anything, but I don't know what is the latest stand.
Yeah.
Yeah.
What about Ethereum, which you taught yesterday?
ETH.
So is it like the same like Bitcoin? Like can we go to
Yeah,
the
same.
bank and-
Not the bank.
You said that like withdrawable, like to real money. We can only build blockchain system with that. Yesterday you told as well. So is it similar to Bitcoin? Bitcoin, like, can we exchange it with money?
Can I exchange with money? Yes, all currencies you can exchange with money. You have to go to a exchange that supports that currency.
By making these blocks, are we providing more security, or what are we actually doing?
Yeah, so good question. What are we doing with all these blocks? So essentially, these blocks, they are not improving or decreasing security. The blocks is something like, just think of it, you are making transactions and everything is recorded in a transaction. That's it. So it's just a way of record keeping. But yeah, there has to be security. And we'll say how this is inbuilt security when we look into, we'll be talking about it. Yeah, so think about it, that when we require so much computing at our end, it's not very profitable for us, normal people, to get anything out of this mining, right? So there's a concept of, mining pools. So people collectively mine the cryptocurrencies. So what it says is that you have to give your computer someone or computing resource. I would not say computer, I will say computing resource. There are then other people, they will share the computing resource, and then this is these together would form a mining pool. So there are many people in this pool, many resources that are contributed, and that makes things, you make a sizable amount of computing together. Question?
So if I were to start Bitcoin, like mining Bitcoin right now, what should my first step be?
Oh gosh. No, I think it's quite risky, first of all. To think that you will be able to get something, to be very honest, I'll not give you any guidelines or, give any suggestion, recommendations or anything of that sort. But,
But how is it done? Like, how is it started?
How it started is that you can use your computer, download the client. You can download a Bitcoin client. You can participate as a miner. You can. Whether you will get a reward or not, that is not guaranteed. That's what I'm saying. But you can download a Bitcoin client. Huh?
For what I would get rewarded? For what I do, would I get rewarded?
I don't know. I mean, look, will be competing with all these people, all these pools. So the pools, so there are some pools, you will see that these are the pools which are generating the most number of blocks. And if you ask me the size of the pools, maybe in the afternoon, let's do this exercise. We can really look into some of the statistics about Bitcoin. We can do that. All data is available, so we'll go. You can ask me a lot of questions, and we'll do this in the tutorial session. Okay, so you see that this unknown could be anything. Like it could be, it's not very clear whether these are, pools or there are, mining farms or whatever. But you see that there are so many pools written. You see, Mara pool, and then Ant pool. Yeah. Did they have SBI crypto? This SBI is very different from the SBI bank. Please don't confuse. It's very confusing, but this has nothing to do with the State Bank of India. No. So what I'm trying to say that these are real big organizations who are doing the mining thing. So it's not, you will be competing with these people. Okay. So one thing that I did not say yesterday, and I think it's very important to mention, is the concept of double spending. Double spending. So let's see what's the meaning of double spending. Say, for example, I have, say, 10 Bitcoins with me, and I want to give it to one of you. Who wants Bitcoin? 10 Bitcoins. What's your name?
Raj.
What?
Raj.
Raj wants 10 bitcoins. So I give Raj 10 bitcoins. No. I have only 10. So what's your name? Ram Kumar. So I'm giving 10 bitcoins to Raj and 10 bitcoins to Ram Kumar. Is it possible? No, right? That's called double spending. I'm trying to spend to both. It's not possible because I have only $10 with 10 bitcoins with me, right? So then the question becomes how this is taken care of in this system. What if I have two transactions made, one to Raj, one to Ram? How can the system say, you are double spending? It should prevent me do both these transactions because I have only 10 bitcoins with me. So the way it happens is that suppose the first transaction is with Raj. So I give Raj this 10 bitcoins and this is added to the block, suppose. And then I give this other 10, again, I make a transaction with 10 bitcoins to Ram. And this is also added on my chain. Okay? Now, yeah, that's what I'm saying. It's not possible. Why it's not possible? So when a miner is adding this this block on the chain, when the miner is adding the block on the chain and it is broadcasting it, if there is a group of people who are able to see that, they will think that this is the correct block. So further, all the blocks are added on top of the block B. Okay? If I see B first, I can mine on B. But if I see C first, then I will mine on C, right? I cannot mine on both because I'm seeing the same transaction in both the ones, so I know that it is not possible. So imagine for a sec that there's a half of you over here on this side, you have seen B, you have created your block on B. On this side, you have seen C first, you have mined on C. Now what is happening is that there's what I call is possibly a fork. So maybe you can think of it can create a fork. So that will be B fork and this will be C fork. And this goes on, the B fork, people on the B fork will start mining on the B upper fork, and then the ones on the lower one will mine on the lower fork. But then Bitcoin has this rule that says like I will choose the longest chain to mine. So whenever I see that the first one has 1, 2, 3, 4, 5, 6 blocks, and this one has 7 blocks, I will actually mine, as a miner, I will mine on the longest chain. So I will add on this chain. And naturally, the others will also see that a bigger chain, so they will also mine. So that upper chain will get cut off. So essentially, only one, either Raj or Ram's transaction, my transaction with one of you will be in the blockchain, not both. It is not a benefit. I would say this is a choice to stop. Yeah, to stop. So you have to decide, because there could be forks, right? There could be forks. As I said, this is a situation where there could be fork. That together you are seeing two different things. You have come up with two different things. You decide and you decide together. So there is a fork. But you have to resolve forks because you don't want forks, because you have to have like one chain. And that is why this is a fork resolution strategy. It could be something else. Bitcoin chooses the longest chain. Ethereum chooses the heaviest chain. It's just that. Yeah, I mean, that is the choice of the, from the Bitcoin, design. Yeah, that's a good question. Why did they go for a fork choice like this? So some blockchains, they do not allow forks at the same, at all. That is another design. Okay, I'm not going to talk about it, but just letting you know, forks can happen. I'll come to you. Forks can happen in many situations, and there should be some fork resolution strategies, and you can choose one. But there are some blockchains which will disallow forks. So they have some mechanism which will essentially not let forks happen in the first place. Yeah, algorithmically it is decided. Question?
Ma'am, as it's written on the slide as well, the 50% consensus protocol, the Nakamoto coefficient, there was earlier a pie chart showing the mining pools. I just had a question. Was that pie chart of the whole blockchain, like how much a mining pool contribute? Because if that's the case, just it gives the Nakamoto coefficient of 2 to the Bitcoin blockchain.
It gives what?
Nakamoto coefficient of 2. Like it only needs 2 bad parties to like completely change the blockchain.
2 bad parties. How?
Yeah, because like can.
Yeah, sure. Yeah.
Yeah. So in here, it just needs 2 parties to merge together to like create a bad fork in the blockchain.
Oh, yeah. So that's a good thing. Yeah, it is possible if 2 of these blocks, if there's 2 of these pools mine, the 2 of these pools join forces, they can revert possibly. And it has happened. There was one scenario where this there was at one point of time there was a pool which was more than 51%, and then somehow they had I can't remember exactly how, but they had introduced some mechanism by which it was countered, and something happened. I can't remember what was it, but I can come back to you. But yeah, it can happen that if there are 2 big pools coming together, then they can get a 51% attack. The thing is that with pools, when there are pools, there are various rewards within the pools, reward strategies within the pools as well. Say, for example, all of you are part of a pool. Your pool might say, only if you mine a block, I will give you some money. There could be some pools which might say, like, you have to contribute to the computational resource. There could be some pool that would say, like, okay, to start with, I will give you I will give you some Bitcoin, but if you fail to do, I will slash it. So there are different strategies within pools as well. The other thing that I wanted to say is this 51% thing that you saw just now. There has been analysis where people have been able to show with under certain strategies, you can get 33% attack as well. I'm not going into all that. That will essentially take a lot of, we don't have enough time. But just telling you that there's a lot of interesting problems. And these problems, let me tell you, these problems, even if you are in your year 3 or 4, these could be also good BTP projects, to be very honest, to look into how, some of the attacks work on some of these things. Either pools or, what sort of strategies people take, miners take. Okay. Questions? I'm actually going pretty slow, but it's okay. Okay, so this is Ethereum's proof of work. Okay, what was I about to say here? I think I said everything. Okay, one thing that I did not say is that if there is a chain which is, part of the chain of the fork which is removed, there are some orphan blocks. And with the orphan blocks, it's like, it comes back, the transactions come back to the mempool, and again, the strategy is that you choose from the mempool. There are many things to do on the mempool side of it, like which transaction should I choose? Oh, this I did not say. Actually, there's so much to say with this sort of things. It's each of these would be a 1-hour class in my normal course. I'm coming to your question. So the miners miners not only get the reward, but they get some transaction fee from the transactions they are putting in the block. So there is also a transaction fee. And there are different ways even miners play it out. Why? Because if they are including high value transaction, they would get more transaction fee compared to a low value transaction. And this could again create an imbalance, right? So there are different ways to counter these sort of things as well. So there's a lot of these, and I said, there's a lot of questions around incentives and so on. It's really very, very fascinating. Yes, question. Who had a question? You, yeah.
Last time you said who has something like extra. What if they have blocks are equal, like 6, both are 6? How it works? Like?
Yeah. So again, it will grow. At some point of time, one will be chopped off. Okay. So this is Ethereum. Ethereum essentially takes a different strategy. It says like, I will go with the heaviest block. So, for example, if you look here, if it was Bitcoin strategy, then Bitcoin would have taken the last one. And heaviest means you will count the number of blocks. Say, for example, yeah, so it was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. No, I think there's something wrong. I think the last one, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Main chain according, I think, the first one should be the main chain according to the first rule. But according to this protocol from Ethereum, you see the heaviest one. Heaviest chain is the one which has a number of blocks. So 4B has all these blocks in its chain. So essentially 0, 18, 0, 1B, 2C, 2B, everything is in that chain. So that is heavy, heavier than the one on the top or the bottom one. So Ghost essentially takes the strategy. Ghost is a protocol. It's called the greedy heaviest observed subtree. It's the number of nodes that are in the subtree. So all the nodes, let me see if my cursor works. Okay, all the nodes, nodes with from 0 to 2B, that's the subtree over there. All these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes in the subtree and then 4B, and these have all 6 surfaces. The longest chain is actually the last one, not the upper one. So this is just a strategy that Ethereum used to use. Now they have moved to proof of stake. Okay. What Ethereum does, instead of just having completely throwing away the blocks that were not added, they have something called an uncle blocks. And so on. So I'm not going into the details of all that, but let me talk about a different type of consensus algorithm for these networks, blockchains. And let me talk about the proof of stake protocol, and I will stop there. So proof of work essentially is very computationally heavy. As I said, you have to do a lot of computing, and these are wasteful computing. You don't get anything out of those. You just have to solve puzzles. So that's why people started thinking, this is so so much against in the environment. Let's do something else. And this proof of stake is another idea that they came up with. The idea of proof of stake is very simple. What is it? Think about it. If you have a stake on something, you are more likely to be honorable to that. So, for example, if you know that, if think of a venture, you have started a a venture with some of your friends, and you have put in, say, some amount of money. Your friend has put in some amount of money. You want to come up with a software startup, possibly. So, the more stake you prove, whatever profit or loss happens, you share proportionately, right? So the same idea. The more stake you put in, the more it just says that you have more belonging to that particular thing. So it's more likely that you will work harder towards the good of that particular project, right? So this is the same idea. So the rationale is that users having more stake have more interest in running the system. So they are the ones who would be more honestly behaving in the system. So that's the whole idea of this proof of stake. And that's why what happens in proof of stake is that instead of miners, they call validators. So validators, they would stake money. And the ones which have put more money have higher, and they have formed, once they generate blocks, if they have staked money, they have higher probability of chosen as the successful miner. Okay, I'll repeat. So what happened in Bitcoin was that you had to solve a lottery to get that reward, or get your block published. In this case, what will happen is that if you have put more money, you are more likely to get your block accepted, chosen by the system. That is the idea. So the higher the stake you put, the better is your chance of getting a reward back, or get your block on the system. That is the main idea. So is this idea clear to everyone? Yes.
Someone will get more stakes, he'll get the reward. Again, he's getting the rewards, he's getting the stakes. So it will be like being centralized after some time.
Exactly. So that's a good point. So what can we do to, just making the rich get richer? And there are different ways to deal with such a question, such a scenario. And so essentially what will happen is that it will get centralized, right? So we don't want that to happen. So different blockchains essentially do deal with the same problem, as you said, in different ways. And we are going to see how Ethereum does it. But that is a very good question. So participants, okay, so this is what we said. Participants vote on newer blocks. Yeah, by those who have more stake would have a higher chance of being successful, but not always. So it is again a probabilistic approach. It's not that amongst the people who have put their stake, I will choose the highest one. It is still a probabilistic approach where that person or that node will have a higher chance of getting selected. So that's essentially a probabilistic technique, not a deterministic. It was not deliberately made deterministic to address that question. So the way it happens is that there is a leader, and this leader is selected at random from amongst the stakeholders. Say, for example, there are 10 stakeholders who have staked. Then a leader is chosen at random. The leader is made the block proposer. It proposes the block, and everyone looks into the block. They add their attestations saying whether the block is correct or wrong. And if there is enough attestation, then the block gets accepted by the system. That's how most of the proof of stake protocols work. Now there are issues with this, and we are coming to that in a bit. So this leader election is something that is a question. So you will ask me, how is a leader selected? And this leader is selected in a very public way. I mean, everyone will, there's a mechanism to make sure that whoever is chosen as a leader is the correct leader. And the other thing that you have to ensure is that you cannot predict the next leader in advance. There are two things. First thing is that the leader is selected at random, but you cannot predict the next leader. These are not easy to do. When I'm saying all this, each of them have mathematical proofs to demonstrate that these are correct. So these protocols that I'm just saying, these are, these have been well studied and well analyzed. But I'm not going to talk about all that. But to be very clear on this, that this is done publicly. It's not like I'm choosing you as my, as a leader. That does not happen. It's a system which chooses a leader based upon the stake. And then the output is visible to all participants. And the leader cannot be predicted in advance. And so, because the leader cannot be predicted in advance, there should be a leader selection mechanism that can prevent that. Now, how do they do? That's for another time. Okay. Yeah, so validators are again chosen based upon the number of coins they have staked. And then the validators submit if the transaction, if the block is correct, then no worries. They will attest it. If it is not, then, the block is not added and the stake is slashed. If you are dishonest, then your stake is slashed. So that's why you have to be, do things honestly.
Are you using any probabilistic model in it to select the leader?
Yes.
So what kind of distribution is it?
It's not just a distribution. There's many things that you have to keep in mind. It's just not selecting something. You have to select something that cannot be predicted. Yeah. So there are different algorithms to do that. So I'm not going into it today. But, we can have another chat on that. And I will give you some resources at the end of the session so that you can yourself go through these things. Okay, then there are attacks. As we saw, there are 3 attacks on the proof of stake protocol. The first one is called nothing at stake. Where the blocks, where the miners can simply mine on multiple blocks to improve their chances. But since they, they can just keep on mining and just try out their luck. But this can be prevented by introducing a penalty that, that I said, you can, if you are not doing it correctly, then your money will be slashed. So that is how these proof of stake protocols do away with this problem. Then there could be other attacks called a grinding attack, where you can recreate a block multiple times until it is likely that the miner can create a second block soon afterwards. And as I said, you have to make sure that you cannot influence the next leader. Because if you knew who the next leader is, then you can, you can somehow, if you knew who the next leader is, you can take drastic measures to stop that leader to create the next block. So there could be different attacks on this. Okay. The third type of attack is that long-range attacks, where you can bribe a miner who can hold a large stake and rewrite the history. So, for example, I'll take a miner who has a large stake and, I'll change the block, I will change the key, and I will rewrite the history of the entire blockchain from, not entire, but at least quite a few blocks in the past. And that is why most of the blockchain take hold of something called a checkpointing. Checkpointing means after a certain time, whatever I have written, whatever is written on the blockchain remains. You cannot do away. You cannot rewrite history. So what this attack says is that you can rewrite history. However, what you could possibly do is that you can checkpoint. Say, for till Friday, whatever has been done till Friday is whatever I take. Again, the next time. So before this Friday, whatever happens, the history cannot be changed. So in that way, You can deal with the long-range attacks. And then there are other ways where you could have a bribery attack, where you could, bribery attack could be present in different blockchains, but it's also present in the proof of stake algorithms where you can, the attacker is financially induce some validators to approve their block. So they might give some bribes to the validator and say, look, you have to attest my block. So there are all these attacks with proof of stake, and these are done away with Ethereum, in Ethereum. So Ethereum started as a proof of work blockchain. And it was facing the same problem. It was computationally very heavy. People were not liking it. The community is not liking it because it's not environment friendly. So in 2022, it moved to a proof of stake blockchain. And this is before that, this is called a merge. You see that thing, it's called merge. Now it is completely a proof of stake blockchain. Now, something I hadn't said in yesterday was that anything you want to, any way you want to change the structure of the blockchain, it needs to be, it will induce a fork. It's called a hard fork. What does a hard fork means? Like, whatever a blockchain does is essentially coded in your client, right? Your blockchain client, as we were talking, that software. Now, if you want to change something, then this has to be changed completely, right? This decision is not an easy decision because you really have a different mechanism to verify. So it's not very clear how I would verify the previous or the historical blocks. So that is why taking a hard fork decision is a decision that the community has to take. And because there's no one person, or not one country, or no one government, right? There's, it's democratic, across the whole world, anyone can participate in this. So it's very important that such decisions of making forks is taken in a way that is acceptable to the community. And this, in the past, Bitcoin also has some forks on Bitcoin. But this Ethereum fork was really exciting fork because it moved from one type of consensus to another completely. And before it moved, there was something called a beacon chain, and they ran extensive. Beacon chain was completely proof of stake based protocol, and they extensively ran experiments and so on before they made that merge. And Ethereum essentially ensured that everything, all the history is preserved, and everything is configured correctly so that after this transition or after the merge, things work pretty fine. Now Ethereum has a proof of stake blockchain. Okay, so I'll just talk a little bit about the Ethereum's proof of stake, and maybe we can stop there. So the way Ethereum proof of stake works is that if you are a user, you would deposit some ETH into the deposit contract. And in this case, a 32 ETH, anyone who wants to be a validator, who wants to be in the system, who has to generate the block, it has to deposit this 32 ETH, and then it has to run 3 pieces of software. An execution client, a consensus client, and a validator client. When I say client, these are all, you can think of things as programs, okay? Now, once activated, essentially what activation means is that it has to get accepted. The validators receive new blocks from the peer nodes. So as we said, when peers construct blocks, these are sent across the network, and these come to the validators. So once a new node is added, it has to wait for some time for activation. And then after that time, it can accept blocks from the peer nodes. And the way it happens is that these transactions are delivered in the block, are re-executed to check the proposed changes in the Ethereum state are valid and the signature is valid. So tomorrow I will show you how a tomorrow or today possibly, I'll show you how the Ethereum state looks like. I'll show you the entire data structure. It's very interesting. So what they do as a validator, they would check that these transactions have been executed correctly and the state change has occurred correctly. What it means by the state is that state is essentially information regarding the accounts of all the accounts that are present in Ethereum ecosystem. So that is maintained in the state. That together form the state of Ethereum. So it checks that the state is consistent. It has been not consistent, it has been updated correctly. So yeah, it is consistent with the new block. All the transactions are correct. The state transition has been is correct. This is what the validators would check. And if both things are right, they will attest it. They will say, yes, this is a valid block. With this valid block, the state change is correct. So yes, attestation. So the validator sends a vote. And then this transaction, or the block should receive enough attestations. So what Ethereum does is that it divides the time into epochs, and there are 32 slots or 32 slots, and each slot takes around 12 seconds to get finalized. So in whatever Bitcoin was doing in 10 minutes, now it's like 12 seconds. And then you have 32 slots in one epoch, and every time a validator is randomly selected to be the block proposer in that slot. So think of it, there are no chalks here. Oh yeah, there is. Or maybe, yeah, it's something like this. So there are epochs, and then there are slots within this epoch. So every time one validator is randomly selected to be a block proposer at every slot. So there's one block proposer, and this is randomly selected. And this validator is responsible for creating a new block. So this will create a new block, the validator, and it will send to everyone. And then it should get enough attestation on this block. The good thing about Ethereum is that the validator is responsible for creating the block and sending it out to the other blocks. And a committee of validators is randomly chosen whose votes can be determined. So they have to be endorsed by this set of nodes who have been randomly selected. But they are selected based upon the stake that they have put in. So it's not one person. They are choosing a group of nodes to form a committee. So this forms a committee. So this committee is responsible to attest the blocks. And because this is chosen with a, it's not just one, so it's that phenomena is not there. You have enough people who really care about the system being chosen so that they can attest. Because if you care about the system, if you have high stake, then possibly you would attest correctly. That's the main idea. So the committee of validator is randomly chosen, whose votes are determined, and the validity of the block being proposed. And the committees are divided up. The committee divide up. So this slot, there's one committee. This slot, there would be another committee. This slot, there would be another committee. So the same node will not be attesting in all slots. Do you get my point? Same node will not be. It is divided so that the validator set, whoever wants to validate, validators should stake actually, should put up a stake. So they cannot do it multiple times with the same slot, but across the slots they can do. And why is this the case? The only reason is that they want to give chance to everyone who has staked to have their say. and at the same time they don't want to make, someone who has stake and doing it multiple times. That's what they do. And Ethereum's proof of stake again can be shown to be correct. Yeah. Yeah, if you are giving an incorrect thing, then your stakes will be slashed. Yeah. So yeah, so this validators, whichever validator is behaving maliciously, it's getting slashed. But generally, generally these validators, because they have high stakes, they tend to be more fair and more, they tend to be honest in their decision. Yeah, also the block proposer, if it's proposing an invalid block, then it's also gets slashed. Okay, so this is just a picture which shows the, some of the existing projects that are essentially running these things. So for the execution node, there are, Nethermind, a software from Nethermind, a software from Besu, a software from Geth or Aragon. They are running this execution node. The beacon node, again, this Prism, Teku, Lighthouse, these are all, clients. So you can choose, nodes can choose either of these clients. So that's the thing. When I say different clients, all these names, they have just different, implementation. They're doing the same task. They have different implementation. And the reason they have all these clients, a variety of clients, is that if there is one client which has gone rogue, you can rely on other clients. That's the reason. So the Lighthouse project is an Australian project. I know their team quite well. So they along with the others, so they are both the beacon node as well as the validator node. They are they run these protocols. But if one of them gets somehow manipulated or corrupt, then you can just forget it. It will just be gone, and then you can rely on the others. Okay, so that's the Ethereum data structure. Okay, maybe one thing that I will talk about. Maybe I'll stop with two things. 2 slides. The first is that there's another protocol which is that has another type of consensus, which is called delegated stake, proof of delegated stake. And in this case, only the validators, they themselves do not stake. They will ask for others to stake on their behalf. And these are called the delegators. So essentially, if I'm a validator, I can take, some of you, and I might say, like, you can stake on my behalf, and if I'm I'm getting rewarded, I will give it to you, give you a share. So this is another mode, because sometimes a validator might not have enough to stake, so it is getting a few delegators to join. And the Stron and US are using this model. And there's another thing called a proof of history. I'm not going to talk about it. Solana, which is also a very well-known blockchain, uses this proof of history. So there's a lot of other proof of X kind of protocols. There's something called a proof of burn, proof of authority, and so on. What I will suggest that you have a look into this, there's this, can you see this? It's not visible. Let me see why it's not visible. Yeah, so this paper essentially talks a lot about these different consensus algorithms that are there in the blockchain. It's from 2019, but this literature has improved over the last few years. So, you can have a look just to get some idea about how different consensus algorithms work. Okay, with that, we'll stop for this session, and I'll see you in the second, after lunch, where you have a lot of questions. You'll ask me questions, and we can see online how the stats look like. Okay? And if you have any questions, please feel free to ask me. You have my email, right? It's in my first slide. So, please ask or email me if you have any questions. And catch up with me during the tea, and ask questions. I mean, that's not, that's also the time when you interact with me. Okay. Thank you very much.